All right, so we're going to look at some stuff about 3.2, which is on regression. So in regression and the line of best fit, we're going to try to find a line that find a linear line, y equals mx plus b, that best fits the data. So we're going to try to take a scatter plot that has a bunch of different ordered pairs, and we're going to try to approximate it with a line. So our biggest objective is we're trying to quantify this relationship between the explanatory and the response variable, so we can predict the average response for all the subjects with a given value of the explanatory variable. So a correlation, you could have a high correlation. If I have an R equal to 0.92, that's a strong relationship, but that doesn't tell me if X value for the explanatory is 3, the R being 0.92 does not tell me what a predicted Y value is going to be. So in a regression, we try to find a linear equation, mx plus b, that will be able to predict the average response for subjects with this given value. So a regression equation is simply going to be, in stats, we call it y equals ax plus b. So in algebra, we say mx plus b with m being the slope, but in statistics, we use a for the slope. You will also see a lot of times this written as y hat equals ax plus b, where y hat is the average response, or average value of the response variable for a given explanatory variable. So a and b are just simply slope and y-intercept. X is going to be the explanatory, and y, or y hat, is going to be the average value of the response variable. So here is an example that is comparing the lifespan versus your hours worked, we'll say, per week. So you can see all the blue dots are the data that were collected, and then through some math, we figured out that there is a regression line. There is a line that best fits the data that looks like this. So you can see this is a positive sloped line, which would seem to think that the more you work, the longer your lifespan is going to be. But you can use this line to kind of approximate the average response. So what would you predict the average lifespan would be for someone who works 30 hours a week? Well, here's 30. So if I go up to my regression line, now there may or may not be a point there, but we can go to the line and we can figure, all right, well, what's the average value here? So what is that value? Somewhere, I don't know, 55-ish. So we could say y hat is 55 years. So what you're figuring out is if you had lots and lots of people with 30 hours a week worked, on average, they would live to be about 55 years old. That's what this regression line is finding. So the big question is, how do we find this regression line? Well, there is a way to find it using some formulas. And the big things you will need is you'll need the mean of both lists, your X and Y list, and the standard deviation of both of those lists, and also your correlation. So remember, when you have all these ordered pairs, we have all these X and Ys, we have all these values, there is some average for this list, and there is some average for this list. There is some standard deviation for this list, there is some standard deviation for this list. So based on that and your correlation R, you can find the slope and y-intercept of your line. So the slope is simply given by this equation. A equals R times the quotient of the two standard deviations, S of y divided by S of x. And if you remember what normal slope is change in y over change in x. So this is kind of our change in y, this is kind of our change in x, multiplied by this factor of R, which is talking about how strong your correlation is. Then your y-intercept b, you are given by y bar, which is the average of the y list, minus a, which is the slope you just found, times x bar, which is the average of the x list. So if we look at an example here I have some of these values. So we are given a set of bivariate data. Remember, bivariate just means two variables, x and y, with the following summary statistics. So here are all the values. So I put the data into the calculator. I got this for my mean, this for my standard deviation, this for my other mean, this for my other standard deviation, and this for my correlation. So if I want to find the least squares regression line, the slope of that is going to be r times s of y over s of x. So I can just plug those things in. So that's negative 0.881 times s of y, which is going to be 1.7, divided by s of x, which is 2.3. So now this is just numbers that I can calculate. So this is going to give me negative 0.65. And now for B, remember, is going to be y bar minus ax bar. So B is going to be the y average, which is 10, minus A, which we just found, which is negative 0.65, times x bar, which is 12. So again, I could just do the same thing. It's going to be 10 minus a negative 0.65 times 12, which should be 17.8. Now, this is not my regression line. This is my slope and this is my intercept, but I still have to make sure I write the final answer. Y hat equals negative 0.65 x plus 17.8. And so now if I have an x, I can find the predicted average response value for that variable. Now, most of the time, quite honestly, we will not use the formula with all these lists. We'll actually use the calculator. So instead of using the formula, most of the times we'll use our technology. We'll use our graphing calculator to find the regression line. So there is a function in your TI calculator. It's called the linear regression function, ax plus b. So what I've done is I've made a second video that's going to show you how to do the regression. So what I would do is I would pause this video and I would go and I would look at the second video, which is going to help us to find that linear regression line in a TI calculator. So go ahead and hit pause, jump on the second video. There's a second video that kind of goes through how to find the regression line in your calculator. So once you have it, once you have this regression line, once you have this y hat equals ax plus b, then we can calculate what are called residuals. Now residuals is going to be the difference in the actual value versus the predicted value. So if we want to think about this as a formula, the residual is going to be your actual value, which is y, minus your predicted value, which is y hat. So if I actually had a data point on there, let's say the data point was x equal 2, and it gave me a y of 5, but when I plugged 2 into my regression line, let's say I got a y hat of 4. Well, in this case, my residual would be 1, because it's going to be 5 minus 4, which is saying my actual value was 1 higher than my predicted value. It could be negative if it's the opposite. If your predicted value is bigger than your actual value, you can have a negative residual. Now, why do we do residuals? Residuals are really important because a plot of residuals will tell us how good a model a linear regression is. So a plot of residuals is going to be a graph plotting the x values and the residuals. And what we're really trying to look for is we are looking for a really scattered graph. For the more scattered it is, the more scattered my residual plot is, the better fit a linear model is. So if you remember that there are lots of kind of patterns. You can have quadratic, you can have sinusoidal, But the closer that your residual plot is to looking really, really scattered, the better idea that a linear regression is an appropriate model. So if your residual plot shows a straight line, that is not good. We would prefer our residual plot to be scattered, kind of all over the place, because that's showing that there's not really a pattern in one being bigger than the other, the residual or the predicted versus the actual. So what I want to do here is let's do an example. I want to find a regression line for the following data and figure out which one has the largest residual. So the first thing I'm going to do, here is my x, here is my y. So I'm going to go ahead and put those in the calculator, and I'm going to figure out what my regression line is. So again, you can refer to the other video that I made that is attached to this section to see how we would find that regression line. So I went ahead and put it in my calculator, and I would encourage you to do the same thing. Hit pause, make sure you get the same thing as I get. So I'm getting 0.02x rounded to the nearest hundredth plus 19.89. So that's my regression line. So to find my residuals, what I'll have to do is I'll have to take for each one of these, I'll have to find the predicted value. So the predicted value, remember y hat, is I am going to plug all the x's in. So to get the first y hat for the 345 pounds, just as an example, what I'm going to do is I'm going to take that 0.02x plus 19.89, but instead of x, what I'm going to do is I'm going to replace it with 345. So we'll do 0.02 times 345 plus 19.89, which is going to give me 26.79. So that's my predicted value. So what I'm really trying to do, though, because eventually I'm trying to figure out which one has the largest residual and then find a residual plot. So I'm going to have to find my residual up here. So remember, the residual is going to be y minus y bar. So in this case, that's going to be 24 minus 26.79. That's going to give me negative 2.79 for that residual. That means the actual value was 2.79 smaller than my predicted value. So now I'm just going to go ahead and I'm going to continue. I'm going to plug all these x's in to get all my predicted values. So I'm just going to go ahead and write them here. You can obviously calculate them. You can plug all these values in for my regression equation. But just so you're not watching me plug these in every time, I'll just kind of write them down. So I get 29.01, I get 26.31, I get 29.01 again, which makes sense because I have the same data, or the same x there. So then I have 30.39, and then I have 40.39, and then I have 60.01, and then I have 46.79. And so now those are all my predicted values. So now what I'll do is I'll take all of my lifespan values that I had and I'll subtract it from those predicted values to get my residuals. Again, just to have you not watch me calculate these, I just go ahead and do those residuals. So that's negative 1.01, negative 8.31, negative 0.01, 0.61, 2.61, negative 12.01, and finally 0.21. So now I have all these residuals, some negative, some positive. So my goal is when I make my residual plot, I would prefer there not to be any pattern. So what I'm going to do when I make my residual plot down here, we usually use something like this. This is the 0 on the y-axis, and then you can see my smallest residual is negative 12. So maybe I go negative 5, negative 10, negative 15, 5, 10, 15. And then we usually put this middle line because we like to see if they are kind of scattered all around that line. And then we put another kind of x-axis just kind of at the bottom down here, and this is where we'll put our number of pounds of bugs, 8. So my first point, what I'm going to do is I have 345 for the x and negative 2.79 for the y. So if I go ahead and I scale this, this goes up to 2,000. So this will be 1,000. So this will be 500. So and this will be 1,500. So if we think about 345 and negative 2.79, that's somewhere around there. Our next one is 456 and negative 1.01, so somewhere around there. Then we have 321, negative 8, so somewhere around there. We have 456 and negative 0.01, so that's really, really close to this one. Then we have 525 and 0.61, so that's a little positive there. We have 1,025 and 2.61. We have 2,006 and negative 12. And then we have 1,345 and 0.21. So this is a small data set, obviously. But if I look at it, I don't see a real pattern. I mean, you might say there's kind of a curve pattern here, but it's pretty scattered. Some are above the line, some are below the line. So I don't see a real definitive pattern. So I'd say the no pattern, since there's no pattern, no clear pattern, linear regression is a good model. So we don't need to look for a different model. Linear regression is a good way to go. What you really don't want to see for a linear regression, you don't really want to see a really straight pattern, right? You don't want to see something where it is just really, really clear. That is bad, okay? You want the residual to be different. So let's go ahead and look at another example. This one is about the number of years after 1975 and the number of students per classroom. So we want to find the regression equation. Then we want to find what would be the number of students in 2006 and what's the largest residual. So obviously the first thing I'm going to do is I'm going to put all of this in my calculator. So go ahead and do that. So working that out in the calculator, what I get is y hat equals 1.11x plus 22.05. And so now that's going to be my regression line. So then if I want to know what would I expect the number of students to be in a class in 2006? Well, these are the number of years after 1975. So the question is, how many years after 1975 is 2006? So that's going to give me an x value for this of 31. Because 2006 minus 1975, there are 31 years after that for that to take place. So my predicted value for the number of students in that year is going to be 1.11 times 31 plus 22.05. Now obviously this is going to get pretty big, and if this keeps growing unchecked, we're going to get some pretty crazy numbers. So this is going to give me 56.46 students. Well, that would be really odd to have a class where you have an average of 56.46 students. So again, sometimes a linear pattern will go to a point, but then it kind of becomes something that is not really realistic. So the last part says, what's the largest residual? So obviously to find the largest residual, I will have to find the predicted values for all these. So I'll have to plug in all these x values to get the predicted residuals. So we'll go ahead and do that. So when I plug these in for 0, I'm going to get 22.05. And then again, I'll get 28.71. For the next one, I'll get 30.93. And again, you should plug in a couple of these, make sure you're getting the same thing as I'm getting. 33.15, 35.37, and then 37.59. And so now I have my y values, which are my actually number of rooms I saw, and then I have my predicted values. So to find my residuals, I'll just find the difference. So the residuals, remember, is y minus y hat. So we'll just take all those to find the residuals. So my residuals for this one are going to be 0.95, and then negative 1.71, and then 0.07, and then negative 0.15, and then 0.63, and then 0.41. Now the question is, which one is largest? Well, the largest one, you don't always necessarily want to do the biggest number. It's the biggest farthest away from 0. So this is actually my biggest residual because the predicted value is 1.71 higher than the actual value, or the actual value is 1.71 lower. So this would be 6 years after 1975. Which would be 1981 if you actually want to get the actual year. So one of the big problems that we're talking about with regression is something we just mentioned a second ago, is what happens when this regression kind of keeps going. So here is an example of regression of a height of an infant or a toddler versus their age in months. So what happened is this is some data that was plotted. You can see all these points plotted as we're going up. And so the question is, could we use the regression line to predict her height at 42 months? Well, that 42 months would be right around here. So could we find the linear regression line and find her height at 42 months? Well, probably. We could probably do that. Could we predict it at 360 months? Well, the problem is if we go out to 360 months, that's way out here. So this line is going to keep going and going and going and going. And eventually it'll get out there. But is that as good a prediction? Well, if we do this at 360 months, we could do y equals 71.95 plus 383 times 360 based on this regression line. It'll give me an answer. So if I do that, I will get 209.83 centimeters, which if I convert to feet is about 6.88 feet. Well, there are very few individuals that are over almost 7 feet tall. So I am going to guess this is not a great prediction. And this gives us one of the biggest problems with linear regression called extrapolation. Extrapolation is a problem where you take information. I have data that's from 30 to 65 months. And I'm going to try to use it for some outrageous value like 360 months. That is typically not a good idea. We typically only want to use regression within the data range. So could you use it for 70 months? Probably. That's not too far off, but you want to somewhat be predicting only in these range of numbers that you have data. You don't want to go too far out because, again, just like the number of students per classroom example, this thing keeps growing and going and going and going and going. That's probably not indicative of what the pattern would actually be. So, obviously, if you have any questions on regression, let me know. Make sure you watch the other video some point where you're figuring out how we actually put these in the TI calculator and got our regression lines.